Hi everyone, my name is Luca Savant, and I will now present a work of mine, Gabriele Facciolo and Thibaud Ehret, called Gaussian Splatting for Efficient Satellite Image Photogrammetry. Every day, hundreds of satellites orbit Earth, capturing stunning images of our planet's surface. But turning those 2D snapshots into accurate 3D maps requires specialized, less common and more expensive, quasi-simultaneous stereo acquisitions. Reconstructing 3D maps from collection of opportunistic images, especially quickly, has long been a challenge. What if we could reconstruct detailed terrain models in minutes instead of days? Well, EOGS, which stands for Earth Observation Gaussian Splatting, radically speeds up satellite photogrammetry in the opportunistic image setting. Photogrammetry began with stereo vision, combining two overlapping images to infer depth. That works if the images are taken simultaneously and from specific relative positions. Later, neural radiance fields, or NeRFs, learned continuous 3D scene by training a neural network on many views. These inverse rendering-based models permit to account for the variability induced by illumination changes. Yet, NeRF-based Earth observation models, such as EONeRF, take many hours to train. Gaussian splatting is a recent, faster technique that uses thousands of little 3D Gaussian-shaped blobs, characterized by position, shape, opacity and color, to model a 3D scene. When rendered, each blob is projected from the 3D scene onto the image plane and alpha-blended, building up the image. EOGS tailors Gaussian splatting for satellite images with three tweaks. Starting with an affine camera approximation. Satellites use push-broom sensors. EOGS, instead, fits a simple affine transform achieving sub-pixel alignment. EOGS also uses a shadow mapping pipeline, adapted to satellite images. This requires rendering the scene from the sun point of view to detect occluders and darken pixels behind them, forming a shaded region from the camera point of view. Finally, three custom regularizers are employed. A sparsity-inducing one. Try to use as few Gaussian as possible. A view consistency-inducing one. We enforce consistent color and height for small camera perturbation. Finally, EOGS asks for opaque shadows. We ensure that no texture bleeds into shadow map. Now let's compare EOGS with EONeRF. EOGS is about 300 times faster, with nearly the same accuracy. In areas with dense foliage, it is slightly less precise, but still within centimeters. Moreover, EOGS can struggle with fewer images. Future work could include improving accuracy in low visibility or high variability regions and handling transient elements. EOGS enables near real-time 3D geometry reconstruction of the Earth's surface. Fast 3D updates could transform disaster response, mapping, and environmental monitoring. Thank you for the attention and see you in Nashville.